There are millions of videos trying to explain special relativity. What makes this one any different? Well, the fact that just a few months ago I didn't get it either, and I know what makes it complex for most people. And to illustrate this, I'll be explaining things to my past self. So, let's begin.
Special relativity stems from one fact only. Light speed, no matter the reference frame, is constant. Whether you're on a train or standing still, you'll see the same speed of light. First, let's review classic relativity. If someone on a train moving at 20 meters per second fires a bullet which travels at 120 meters per second, what will be the bullet's speed from an outsider's perspective?
Easy, you just add both speeds up, 140 meters per second. Exactly. Now, what if I replace the bullet with a light ray traveling at c meters per second? What will be its speed on the outsider's reference frame? Same thing, c plus 20 meters per second.
But that's impossible, as light speed is constant for everyone, so it must be c for both.
Okay then, what's the problem?
The problem is that this doesn't make any sense. On the train's reference frame, the light ray traveled c meters in 1 second, but from the outsider's perspective, the light ray traveled c plus 20 meters in 1 second.
If in the train, light travels c meters in 1 second, while outside it, light travels c plus 20 meters in 1 second, how can both observers see the same light speed?
They can't. The outsider's reference frame cannot witness light travel c plus 20 meters in 1 second. For light speed to remain constant, we, or rather the universe, must lower that number to c.
And how do we do that?
Speed is distance over time. To lower it, we can either reduce distance traveled or increase the time it took to travel it. So, we can slow down the train's time or reduce its length. And, in our universe, both things happen. From the outsider's perspective, time inside the train would be slower, and the train itself would compress, a phenomenon known as time dilation and length contraction respectively. To be clear, this is a real thing. It doesn't affect our lives much, as even the clocks of very fast-moving objects like satellites only lose 7 microseconds every day.
That wasn't hard after all.
Now, let's talk about the twins paradox. You know the setup. One twin remains on Earth, we'll call him Elon, while the other, Starman, sets out toward a star, which we'll say is 6 light years away. If Starman's ship travels at 60% of light speed, Lorentz equations tell us time and distance are altered by a factor of 1.25. After Starman sets out, relativity starts affecting their perspectives. From Starman's reference frame, the world around him moves at 60% of c, and due to length contraction, instead of 6 light years, he will see the star as 4.8 light years away. This means that it will take him 8 years to get to the star. Meanwhile, from Elon's perspective, the star remains 6 light years away, and he sees Starman's trip will take 10 years. So, from Starman's perspective, the round trip took 16 years, while from Elon's perspective, it took 20. Thus, Starman will be 4 years younger than Elon on arrival.